Our last little topic here for this unit in work and energy and power, which is power. Uh, a word we use a lot, but in science, not the same things we use in politics or who's in charge of it. So we're not talking about who's in charge here, not that kind of power, not who rules, but something a little bit different related to work. And so we're going to discuss what's power, how do we calculate it, and that's our main little vocabulary word that we have here. All right. So, as a quick review about work, because power builds on work. Remember, work is transferring energy through a force over a distance. So, work is when we use energy basically to move something. We calculate it, force times distance. And we could also say it's a change in kinetic energy. Hopefully, this makes sense because if you change your kinetic energy down here, look, that means you're changing your velocity. And if you're changing your velocity, then you're accelerating. And if you're accelerating, then you've got to have a net force. So if there's a net work being done on something, there's got to be a net force involved as well to cause that change in speed. We measure work in joules. All right, so let's move on to power. Power is one of our formulas that we also have right here. Again, it's not like strength. A lot of times we want to use those words interchangeably, strength and power. And again, in everyday language, maybe so. In physics, it's going to be a little bit different. So power ends up being a rate. You'll notice in the formula down here, it's work divided by time. So using this illustration, the football players, let's kind of compare work and power. So work would be 65 and 55, each push the sled, or they each push their side of the sled 5 yards. So if the sled, assume it weighs the same on both sides and they move at the same distance, they're doing the same amount of work. If number 65 can get from this yard line to the next yard line faster than number 55 can, their work is the same, but their power is different. So the one on the left, number 65, if he can do it faster, would be using more power because he's doing the same amount of work, but in less time. And if we make the bottom of a fraction smaller, our answer gets bigger. Okay, so again, work and power, not the same thing, obviously related, but it's about the amount of time it takes to be able to do that. So again, in summary, it's the same work if you go the same distance and pushing the same amount, but power changes if the time amount changes on. You've probably heard of the unit for this, which is a watt. What? No, that kind of watt. Watt. You see this with light bulbs, and I'll show you an illustration here in just a second. A lot of things that we use in our house that are using energy, those things are used, we look at them in watts or sometimes kilowatts because that's 1,000 watts. A watt is how many joules per second is the amount of energy per second. So I'm going to go through and real quick with a video just to do illustrations that we have on here. We got like a 5-second commercial we have to get through first, but you can hopefully jot some of these things down as illustrative of types of problems that we end up having. So in your house, you might have a certain watt light bulb. And so this is a 25 watt bulb that's illustrating here. That means it's doing 25 joules of energy every second. And so again, the higher the wattage, the more joules per second. And basically that's processing more energy every second. And what we would see with the bulb is that it ends up being a brighter bulb. All right, so if we had a couple of light bulbs to be able to compare with one another, if we knew the amount of joules that were going through it and the time that it took for that amount of energy to go through, we could calculate the power on both of those. So the light bulb on the left, 1,200 joules in 20 seconds. The one on the right, 1,600 in 40 seconds. To calculate the power, we just divide these two numbers together. And the answer we get would be the amount of watts that would be going through the bulbs we'll be using. So 60 watts versus a 40-watt bulb. The bulb on the left is going to be probably brighter. Additionally, it's going to cost you more to use. And so that's one of the things energy-wise that's happened over the number of years is we've changed the type of bulbs we use so that they're actually able to still be bright but use less energy. A car coming to a stop, trying to miss the doggy here. So if it comes to a stop, it might use 10,000 joules of work to slow down and come to a stop. Now, ideally, every car could be able to do that. But if the time changed, that would tell you that there's a difference in the power of the brakes to be able to make that change. So if we did 10,000 joules in 4 seconds, that would give us the power of the brakes, which would be, again, in watts, 2,500 watts. If we have a couple people running up a hill, Jack and Jill, hey, they went up the hill. If they're the same size and they're going the same distance, then they would be doing the same work. And so if they went up the hill and they used 100 joules of energy or 100 joules of work, and they did it in 10 seconds, the power would be, again, work divided by time, or energy divided by time. So 100 divided by 10, and that would give us 10 watts. So it's a pretty simple calculation for us to be able to go through and do these. Some additional examples. So if a weightlifter moves 250 newtons, 2 meters in 0.5 seconds. Again, try to keep these things straight. How much work, how much power? Always, if you come back to your reference sheet, and that's why it's called a reference sheet, you refer to it. If it's asking how much work, we need a force and we need a distance. We need a Newton and we need a meter. So, excuse me. The work is 250 times 2. That's how many joules of work we get. If we want to follow up with power, again, power is work divided by time. We've already calculated our work, and our time was 0.5 seconds. So 500 divided by 0.5, that would be 1,000 watts. Right. Another weightlifter example, 500 newtons, 2.5 meters, 1.5 seconds, and you wanted to say how much power. Notice it didn't ask you work to begin with, so you got to think how much power. Power is work divided by time. It doesn't give us any joules up here, so we're going to have to figure that out, because then we need to go back to work. Work is force times distance. So basically, you could also substitute in FD at the top of this fraction as well. So if you don't know the work, but you know force and distance like we do up here, work is force times distance. So we can kind of rearrange our formula. So instead of work divided by time, we can replace that with force times distance and plug in our numbers. Newtons is a force, meters is a distance, and seconds is our time. So 500 times 2.5 divided by 1.5 gives us 833 watts, which is a pretty good bit of power if you want to compare that to like a standard light bulb that we have there. So again, in summary, power is just a rate of work. How fast is work being done? It's going to be measured in watts, and we have a formula for it on your reference sheet that should be pretty easy for you to use. So we've got some examples to try to work through now, and good luck.